Welcome back, AP, to the last of the information regarding our kinetics and our Chapter 16 content. Last piece of the puzzle that we need to talk about are our catalysts. Catalysts are just a tool, something that we can add to the reaction to speed up, just as it would kind of sound, catalyze the reaction as it is progressing. It has its own way to do that. Each catalyst activates in a slightly different way. We saw catalyst actually earlier with the demonstration of the elephant toothpaste. The way this happens, the way our catalyst works, is by taking, so if we were to look here at the graph, we've got kind of our first reaction, kind of the green swoop here. Wait a minute, delta H here is the difference between reactants and the products. Our products have less internal energy than what our reactants did, so this would be an exothermic process. Yes? Okay, just checking. We've got our transition state here at the top. We've got our activation energy forward, activation energy in reverse. We were to try to go backwards over that kind of transition state. And the way our catalyst works is actually by lowering that top peak. And if you think about it like track, if we lower the hurdles, it's going to be easier and faster to get through the hurdles. And so the way our catalyst will do this is by providing a different pathway, a different mechanism for our reaction to go. And so here our purple line kind of introduces our catalyst. And you'll see it's changed us from a unimolecular reaction or a one-step reaction to now a two-step reaction with a intermediate here in the middle. And so because we've got less activation energy, we're going to be able to get our reactants to turn into products at a faster rate. Now note that this increases the rate both forward and reverse. If we had a reaction that could potentially react back, it could speed that process up as well. Note that, yes, it gets us over the hurdle faster. It doesn't give us more. It's one of the big major misconceptions when it comes to our catalyzed reactions is that we think, oh, well, we're going to get more of our product because it's getting there faster and it's going to happen more efficiently. When we've got a catalyzed reaction, all we've done is said, okay, more particles can get to the product stage in a faster rate, but it's not magically going to add extra reactants that make more products. We just get to that final location at a faster clip. Catalyst lowers that EA, providing a completely different mechanism, completely different reaction than the original that has some new and kind of lower energy requirements or lower activation energies. And there are a whole bunch of catalysts that we can start to see. Here's one for our hydrolysis of an organic ester. Don't worry about the arrows here or kind of the functional groups. We've not covered any of that organic yet, but we can see that we can start to attach this hydrogen to our oxygen on that carbonyl, and then this double bond starts to break apart. We can end up with some resonance where we've kind of moved this cation charge around a little bit. But really what we need to have happen is kind of have that positive charge right here in the middle if we want to kind of add this additional group to finally end up making this carboxylic acid. And so we can see that kind of our slow step is right here. We got to get that cation in just the right spot to make this happen, to be able to get us to that final product. And if that cation charge is in the wrong spot on our molecule, it doesn't attach as quickly, and so we've got to kind of wait until it gets in the right place before it can start to go. One of the ways we can do this is actually start to use, sometimes it's a surface catalyst where we've got a metal, could be platinum or palladium, that's holding our hydrogen molecules in place, allowing our ethylene to attach more quickly. As a result, we see an increase in the rate of that reaction. Here's a little practice problem for you. If you think about what we talked about previously with our mechanisms, we've got kind of a two-step reaction going here where the first step is a slow step or the rate determining step. There's a couple pieces here that we can kind of start to look at. So the first question here asks, which of our species is our catalyst, which is our intermediate, and then given some data, could we actually figure out what our ratio of catalyzed-uncatalyzed reaction would be? Give you a second to try this, pause the video, maybe think about it. When you're ready, we'll kind of talk through it. As you are looking, a catalyst is something that we introduce to the reaction. It does not actually get used up. And so if we're looking at kind of a mechanism as proposed here, we're looking for something that we had as a reactant in the first step that comes back out as a product in the end. And what we've got here, if we look, we've got nitrogen monoxide. Nitrogen monoxide was present at the start of this first reaction with our ozone, and it was present as a final product. And if we were thinking about kind of our Hess's law, we could actually start to cross those out because they aren't really affecting any change on our rate over, on our kind of balanced reaction overall, because they're present both before and after. An intermediate is something that gets made in the middle step, and so we're looking for something that's a product in the first step and a reactant in the second. And so I think our nitrogen dioxide here gets made in the first reaction. We make some nitrogen dioxide and then immediately use it up super quickly with this kind of oxygen molecule. We use it up incredibly quickly in the second step to get back to this original oxygen decomposition. And so if we were to actually add these together, the nitrogen monoxides would cancel out, the nitrogen dioxides would cancel out, and we would actually end up getting back to this overall reaction. If we want a ratio of catalyzed to uncatalyzed, we're just going to take our catalyzed reaction activation energy, divide by our uncatalyzed activation energy, and get ourselves a ratio. And so it would just be 11.9 divided by that 14.0. And so again, just kind of thinking about what a catalyst is and what it does for us in terms of our reaction, for our mechanism, how it changes the pathway, and as a result lowers the activation energy, getting us to those final products faster. Awesome. Our homework is going to be continue working on 16.4. We got that second page to kind of be checking and looking at, and then we've got the study guide that we're using to start preparing for our upcoming assessment. We'll be back, and we'll have a whole day to be talking about what we've kind of covered, get questions answered, make sure we're all good before we kind of progress forward. So I know this was a little bit fast and furious, but we will have plenty of opportunities to make sure we get our learning shored up. Thank you guys, and have a wonderful day.